Well, time flies when you're having fun. It's 11:30 already, and we're ready to carry on with Henry Goodman's presentation. If y'all can find your way back here. Hey, sound up in the back room? And we'd like to thank CEI once again for sponsoring our morning break. And for also sponsoring the stormtroopers that are coming in the back door to shoot you into the meeting area. So please try to make your way back now. We're running 15 minutes behind as it is. Thank you. Well, you heard us, right? Not really. No? Okay. I got a few people back. This is not loud back there. Okay, you get your, you want to put your mic up? I'll get your presentation up. So, see, this is the CEI slide. Click that. There you go. There you go. All right, so you want to just stand at the microphone, or you want to have a headset?
Don't mind, whatever.
Or just right, please, translator. Oh, is that you? No, that's
Ladies and gentlemen, please be seated.
Hello there. I guess we're getting just about everyone. So I'm just going to introduce Henry Goodman, who's going to speak on AES AES67 as it implements with SVIP. And also, one little bit of housekeeping was asked. Connect to Rod and Reel or Rod and Reel 5G for internet access. Go ahead.
Thank you. Good morning, everybody. I think it's still morning. Is it still morning? As I flew in from the UK yesterday, I've really no idea what time it is. So I wanted to talk to you a bit about streaming, more from an audio point of view than from a video point of view, mainly because that's what Cowric does. It's what we do. So I wanted to start off with this slide. Now, I'm not intending to go through 2110 again because that's been done this morning. But I wanted this slide is pretty much how I'm feeling about 2110 at the moment. I did think about doing a little jig, a bit of dance. Obviously, 2110, I think the good thing about that is it's now pretty much established. And certainly from a manufacturer's point of view, it's a significant milestone in the operational and development side of IP. Clearly, there will be more standards that we add to 2110, and there's bound to be a few wrinkles with standards along the way, like there are with all standards. People do tend to interpret standards in different ways, but I'm sure we'll get through those. The key thing from my point of view is that 2110 is pretty much decided. The industry has come together. We've all decided that this is the direction we're going to go in for the broadcast industry, which is fabulous because it means that manufacturers can actually get on with designing products and systems to plug into your 2110 or your IP network. So what I want to look at today, rather than 2110 itself, is a little look at synchronization and PTP clocks. Now, I don't want to steal too much thunder from the gentleman who's presenting about that after me, but I do want to look at different types of PTP clocks. And also then a quick look at working with streams. And we have talked about this earlier with ISO4 and ISO5 and ISO6, but I just want to reinforce a lot of the comments that were said this morning. So, synchronization and clocks, PTP clocks in particular. Well, PTP is not a new protocol. It's a protocol that's been around for a long time. A protocol that's used in many different industries, used in the financial industry, as we've heard earlier, used in industries like for manufacturing, automatic production lines, that sort of thing. Anywhere where timing critical applications is very important. It's actually an IEEE standard called 1588 and was last updated in 2008. Hence 1588, 2008. Now within that standard, and because it gets used for in many different applications, the IEEE do allow different industries to go to them and say, okay, we want to use PTP, but we want to use certain aspects of it, certain settings, certain limited functionality within the wide range of PTP, specifically for our industry. And that's exactly what SMPTE did. And that's what SMPTE 2059 is. It's a set of, if you like, parameters and options within PTP, which have been specifically orientated for the broadcast industry. So let's look a bit about some clocks. The most standard clock you'll find on an IP network is something called an ordinary clock, or an OC. You'll see sometimes written as for short because we do like to abbreviate things. Every endpoint on an IP network will have an ordinary clock in it. Ordinary clocks are slaves to the master clock, the grandmaster clock. We heard about more about grandmaster clocks earlier. The reason that they have their own clock is if there's a failed connection to the master clock, they can freewheel. So each endpoint on an IP network can freewheel and have its own clock. That clock can also be used for other things. It can be used for time of day for the endpoint, or it can be used for digital synchronization within the endpoint itself. So ordinary clock. The next clock that's important is we talked about the Grandmaster clock earlier. The GM provides corrective sync messages to all the slaves. That's basically what it does. It sends out messages to all across the network with time-stamped information on to all the slaves. And part of PTP are two very interesting and clever mechanisms for managing the Grandmaster clock. The first being what's commonly known as the best master clock algorithm, or the BMCA. This has got an interesting thing because it manages which clock on the network is the Grandmaster clock. Across any network running PTP, multiple clocks are on the network. I've already said that you have an ordinary clock in each of the endpoints across the network. But you might allocate a number of clocks on the network that are capable of becoming the Grandmaster clock. And what the best master clock algorithm does is it looks at a set of criteria defined by those clocks. It's like a questionnaire for Grandmaster clocks, if you like, and negotiates which of those clocks is most qualified to be the Grandmaster. And this was an algorithm that runs within every clock on the network, and they negotiate or elect the Grandmaster clock on the network at any one point in time. This is quite clever because it means if for some reason the Grandmaster clock goes away, someone unplugs it, or you lose power to it, or it just crashes or whatever, it means that other clocks on the network can elect themselves to be the Grandmaster clock. So it provides a degree of resilience to the network in terms of PTP. So that's the BMCA. The other important one is the sync correction that PTP provides. Now, I guess, looking around the room, quite a few of you have been to presentations like this before. You've probably seen this slide shown in presentations. I'm not going to go through all the maths involved in this. Not that it's particularly difficult maths, but this represents how ordinary clocks and Grandmaster clocks can synchronize themselves. If you look at this diagram, you'll see that on the right-hand side, the slave side, with 4 timestamps, it can calculate the difference in time that it's taken the sync signal from the Grandmaster clock to reach the slave clock. Once that's calculated, it can program an offset onto that clock and synchronize itself to the Grandmaster. As I said, the maths is not particularly complicated, but it does make one very important assumption. And that assumption is that, sorry if I go back to that drawing, is that the delay between the master and the slave is the same as the delay between the slave and the master. And you might think that's picking hairs a little bit. In cases where you've connected an ordinary clock to a Grandmaster clock directly, that's generally going to be the case. An RJ45 cable, Cat5e cable, one cable between 2 points. The receive and transmit cables within that fiber are going to be around the same delay. They won't be exactly the same delay, but they'll be pretty close. But what's the first thing that we do when we connect a network together? We don't just connect point to point. We put things like switches in the middle, and usually more than one. And as soon as we put a switch into a network, that switches work on buffers to handle the incoming packets and the outgoing packets across your network. And as soon as that happens, the assumption that your slave to master and master slave is the same amount of time is called into question. And this they call packet delay variation time. In other words, the time it takes between master and slave and master can vary due to queuing in buffers. So how do we get around that problem? Well, there are two types of clock that we can use to get around that problem. The first being, and we've heard this name before this morning, a transparent clock. Now, a transparent clock, transparent clock does not require any syncing to the grandmaster clock. Okay? The way a transparent clock works is it passes through itself the sync messages from the grandmaster clock, but it knows, it knows because it can measure itself, it knows the delay that it adds through its buffers. So what it does is it adds that delay into the correction field, which is a small field found within the PTP header. So it adds a time value into that, and then sends that packet on its way across the network. Now this means that when those timing packets arrive at a slave unit at the far end of the network, that unit can look at the correction field, and it will get a number, a timestamp number, which it can adjust its clock against the master timestamp that it sees within the PTP packet, and synchronize itself to the master, including any delays through the network. So it deals with packet delay variation that way. Yeah. The other way of looking at of dealing with delays is through something called a boundary clock, sometimes called BCs, and they are synchronized to the grandmaster clock. Yeah. So the way these work is you have one port which is designated as a slave port, which is synchronized to the grandmaster clock, and all other ports on that boundary clock become effectively master ports for the ordinary clocks or the clocks further downstream from them. The great thing about this is it means that a boundary clock or switch, practically these are switches on the network, will resynchronize themselves to the master. So their clock becomes the master time, and the slaves at the other end, the boundary clock appears to be the same as a grandmaster clock. Yeah. So in effect, a boundary clock will reset the sync at that point in the network. Another way of thinking about it is that any delay values that are upstream of that boundary clock are null and voided at that point. Sometimes people describe this as scrubbed at that point. So any packet time delay variance upstream from that is then reset, and the network moves forward on that basis. So you might ask, well, that's great, Henry, but what does that mean practically? Well, I've tried to provide a very simple answer to that here, and I'm sure the next speaker will elaborate on this somewhat. But a transparent clock obviously reduces the packet time variation. It does give you an end-to-end delay calculation. So in other words, because it's looking at the timestamp from the grandmaster, it will give you all the way through to the endpoint. The time correction it makes is against the grandmaster clock. So it's what they call an end-to-end calculation. Yeah. The downside of using a transparent clock, and I think we covered this one session slightly a little earlier, is that it does increase the load on the grandmaster clock. Most grandmaster clocks have capability in how many timing packets they can handle. So with a transparent clock, you're expecting the grandmaster to do all that work and manage all the timestamps from all the endpoints. But with a boundary clock, one of the advantages of the boundary clock is that the grandmaster is dealing with fewer packets, fewer timing packets, so there's less demand on the grandmaster clock from that point of view. As I said, it also scrubs any delay upstream from that. Disadvantage of boundary clocks. There are some disadvantages of boundary clocks. You don't get anything for free in this world, unfortunately. One of the challenges is because it resyncs to the master, it takes time to do that. So if you want to use systems where you're cascading clocks one after the other, linking them in a line, if you like, boundary clocks tend to accumulate bigger errors when you're setting them up in that environment. So any IP network that you might set up, you could say it would be completely understandable if you had a mixture of boundary and transparent clocks on your network. Obviously, you'll need a grandmaster clock, but you will end up, if you're depending on the design and the topology of your network, with probably, in most broadcast environments, some boundary clocks and some transparent clocks. Generally, you might say, okay, use transparent clocks when you're cascading devices together. Use boundary clocks at major nodes, if you like, or nodes where you're storing ordinary clocks around that node, just as a rule of thumb. And I'm sure the next speaker will talk more about that in terms of topology of the network. Those are the two real types of clocks that we use for mitigating, if you like, these delays that you have across the network in terms of timing. So with 2110, we've got the transport of video and audio across IP network pretty much ticked off. We've got PTP pretty much in the bag, as you can see. So I want to talk a little bit now about working with streams themselves, sometimes called flows. Flows are streams. As you guys will know better than I, you will have hundreds of devices connected to your broadcast infrastructure, if not thousands. And when we go IP, not only will you have hundreds of devices connected to your network, you'll also have the potential of having multiple streams from those devices as well, both sending streams and receiving streams. So it's not unreasonable to expect that you will end up with hundreds of streams, maybe even thousands of streams on your network. We're going to need, as we said earlier, to be able to discover them, to manage them in a reasonable way. One of the other things that we like to do in a broadcast environment is be flexible with streams. And what I mean by that is that you might say, well, in any particular stream, I want 16 channels. 16 channels makes a lot of sense. We're all used to dealing with audio in bunches of 16 because that's what SDI gave us. So it makes sense. You might want to deal with audio in terms of 8 channels per stream, one 5.1 and one stereo signal, for example. We will see microphones with IP interfaces very soon. So that's a stream with a single channel of audio on it. Someone earlier in the session mentioned, well, what happens about MADI, for example? Well, the easiest way to deal with MADI is to have a stream which is 64 channels wide. So you're not actually using a MADI stream, you're using an IP stream, which basically gives you the same as MADI. So we have these different requirements in broadcasting, and they're not all the same. In some parts of the facility, we might want different channel counts. So flexible audio streams are important. There are also other things that we might want to flex. Apart from audio channels, things like packet time, the sample rate of the stream, the audio format or the codec that we're using to format the audio. And remember that with streaming, it's all about senders and receivers. Yeah? So any receiver will need to know will need to know information about how the sender has sent that stream before it can use it. We touched on this earlier. I'm going to expand that a little bit more. Fortunately, we have a standardized way of doing that, which is called an SDP, or it's called Session Description Protocol. And it is a standard set of variables, if you like, that we can set. It's quite interesting because it's almost a human-readable file format. So you can see here that it tells you how many channels we've got in this stream. This is an 8-channel stream. You can see number of channels, 8 channels. It tells you the bit rate, the frequency, the sampling frequency, IP address, where it's come from, the multicast address. So this is, fortunately, a standard way of logging that information for a stream. Now, one of the key points is, in a large broadcast environment, is how you manage those streams, that information. If we go back to having hundreds of streams and devices on the network, they've all got to exchange that information, that SDB information. And in a broadcast environment, that has to be done across different manufacturers. You know? At the moment, probably the most convenient way, or the way we're forced to use it in many cases, is a manual SDB exchange, sometimes referred to as SneakerNet. It's a very American term. But that basically means you take information from your endpoints, from your sender and receiver, and you exchange that information, if you're lucky, with a USB stick into a receiver, and it then tells the receiver what it needs to know to decode the stream that you want to receive. There are other ways of doing it, though. There is RTSP, real-time protocol, that Ravenna and people like Livewire use within their discovery mechanisms. The only challenge with that is that they're pretty much, although they're automatic, in other words, they exchange this SDP information from sender and receiver automatically, they only really work within their domain. So it's not really going to solve our problem of having a multi-vendor environment across a broadcast platform. SAP, Session Announce Protocol, if you're particularly interested, is what Dante use on their network. They use that for their Dante and their AES67 version of Dante. And again, that's an automatic exchange of information, SDP information, but again, sort of proprietary or exclusive within the Dante controller or domain manager. SIP is another discovery mechanism, and that's actually specified, I think, for unicast within AES67. But the reason we're talking so much about NMOS, ISO4, is that ISO4 is a way of exchanging this information. And it's the way that's specified within the JT&M AIMS roadmap, and therefore the way that the industry is going to go. So ISO4 is a framework, if you like, an API that manufacturers like the company I work for, Calrec, can use to develop stream managing applications, if you like, that will help broadcasters manage their streams and manage their networks. So ISO4 is the framework API set, if you like, for discovery and registration. ISO5 is the framework for connection management, in other words, to be able to make those streams, connect them to a receiver, and break them down again. And as we learned earlier, the guy from Cisco, there is also in the works ISO6, which gives you higher levels, deeper levels of network control for switching in the network, so switching sources within the network dynamically, and also gives you a deeper level of diagnostics and monitoring capabilities for the network as well. The I think there was one question earlier about how NMOS and ISO4 works. The way this works is that there is a central server on the network. And that central server sits on the network and keeps information about all the SDP information you have for all the endpoints. The way this works is when an endpoint joins the network, it sends its information to this centralized server, and that server then sends information back about the network to the endpoint. So the endpoint can advertise itself to the server and receive information about streams it might be interested in registering in. Yeah? So there's a central location for that server. It does mean, and quite interestingly, that you could have multiple servers, multiple NMOS servers, for a better way of describing them, on the same network. So it does give you perhaps the opportunity to have a specialized NMOS server for audio, for example, and maybe another specialized server for a router system or a router control system for switching the video, if you want. Doesn't have to be just one server on the network. So this is critical. And this is my main message today, is that the ANWR NMOS, if you like to call it that, ISO4 for discovery and registration, ISO5 for connection management, and following on from that, ISO6, provide an API set, if you like, for manufacturers to develop this sort of management application for you guys. And the reason it's important, why these standards are important, and especially important, probably more important for you than the manufacturers, is it gives the possibility of a manufacturer agnostic management system. So you can have a single place where you can look at your network, look at your streams, and control them and manage them and understand where they're all coming from. It's a practical system-wide approach to managing streams across the broadcast infrastructure. And without that, any large broadcast environment, bigger than maybe one studio, is probably completely impractical to manage. If you imagine a campus-wide environment where you have thousands of endpoints, maybe tens of thousands of streams on your network, having a single place you can go and manage all that, well, without it, you're not going to be able to manage your network. Now, you might ask, where can I get such a thing? Some of you will be familiar with things like Dante and the controller they have, and what they call the domain manager now. There are a number of, if you like, proprietary control systems that you can get. But what you really need is an agnostic control system. So without this agnostic control system, you don't really have a way of managing. And there isn't really one available on the market. I do, however, know that there are manufacturers, I could name one specifically, that are working on providing a management, stream managing application, specifically designed around ISO4, ISO5, with ISO6 in mind in the future. So thank you. If you have any questions, I've been asked to wrap up. Do you want to do questions now, or do you want to leave those till later?
After lunch, when we do all the Q&A.
Okay. Thank you. Well, I'll see you later after lunch.